Hi, welcome to another screencast. This one's about set theory, a question that crops up quite a lot in the syllabus that I teach, and it causes some difficulties, but I think primarily the difficulties come from just not really learning the terminology properly. Once you learn the terminology, the symbols that are used, it's a fairly straightforward topic to grasp. So if you want to pause the screen a moment and read the notation here. Sets are simply a collection of things. Those things might be words, they might be objects. Number work, we are dealing in sets. I go through this in a little bit more detail in one of the other screencasts about surds, but very quickly look at the top here. We've got natural numbers, integers, rational numbers, real numbers, complex numbers. Whenever you're doing any form of calculation, you're working in one or more of those sets. So a set is something that you have probably grown up using. Maybe when you were younger, you put things into groups or sets based on similar properties. This is just a way of formalizing that into notation that does have some connections with logic, Boolean logic, if that's something you're into. There are some similarities between set notation and Boolean algebra. Let's have a look at some of the terminology down here then. I'm not going to read it out, you can read that yourself, but let's just pick up on certain things. We're using notation to represent particular sets, so a letter might be a way of defining a set. If it's a large set, then you may well just define what all of the members have in common. If it's a small set, it might be quicker to list the members of the set rather than the rule. Either way, whenever you are defining a set, you denote it with curly brackets. The common ones are highlighted here, and then you'll very often just find questions that are made up of combinations of each of these. So if A is a set of elements, then A dash is called the complement of that set, and it's anything that is not in the set A that's in the universal set. The universal set is basically just the universe that you are dealing with in any given problem. So A complement is everything that's in the universal set that does not already belong in A. Intersection of two sets is where they overlap or what they have in common. Union is to combine both sets and usually make a larger set. B is a subset of A, means that B is completely contained within A. A set with nothing in it is referred to as the empty set, and it has two different symbols. And then N brackets A is a way of stating how many members a set has. Best way to illustrate set notation is to dive straight in with some questions, so that's what we're going to do. By all means, pause it at any point you feel appropriate in order to read through things, have a go yourself before I talk through them. So one way of illustrating a set is by means of a Venn diagram, and a Venn diagram is simply a diagrammatic way of illustrating the sets. Picture being worth 1,000 words. It's very often a useful way to illustrate what's going on, and you might find it useful when answering given questions. So the box itself represents a universal set, and for the sake of consistency, all of my sets are going to be A's and B's. Now if I was going to illustrate the intersection, A intersect B, the intersection is this region here. The union of two sets is to combine them. So it's everything that's in set A or everything that's in set B or both. So it combines both sets and makes a larger set. Let's look at the complement. A intersect with B dashed means that it's in A but it's not in B. That's this region here. It's in set A, intersect with what's not in B. Well, not in B is everything outside of B, and we want the intersection of everything outside of B with the set A, which is this part here. Let's change that to the union. A union B dashed, and this is one that catches people out. It's in A combined with what's not in B. So it's in A and this is the bit that catches people out. Because they think B dashed, it can't be this region here, but the union means that we're putting all of A together with all of what's not in B. And what's not in B is out here. Combined with all of A. Now, this is simply to illustrate that A intersect B. So these are my two sets. A does not intersect with B, so I would write that as the empty set. That's my attempt at curly brackets, or empty set that way. The next one is to illustrate subset, and we would write that B is a subset of A. There's only so many combinations of these we can deal with. Let's go for A complement intersect with B complement. That means it's not in A, so that's everywhere outside of A, and it's not in B, which is everywhere outside of B. The only place that is both is all the way around the outside. So if we just take a moment, that one here, A dashed intersect B dashed, is the complement of A union B, which was my second diagram. One more then. A dashed union B dashed. Now, if this follows the same connection as these two, this one should look like the complement of A intersect B. Well, A intersect B was up here. This one should look like everything else shaded, if this reasoning follows. So it's not in A, which is all the way around here, and this part. Because that's not in A. Not in B is all the way around the outside plus this one, and the union is to put them together. So as we can see, all of this shaded in this browny orange is the complement of A intersect B up here. So if I link that one there with this one there here, and this one here with this one here, what we have there is an application of De Morgan's law. And let's just write those out. A intersect B complement is the same as A complement union B complement. And what else did we have? We had A union B complement was the same as A complement intersect B complement. We're changing the intersect for a union, and anything that was not dashed becomes dashed or complemented. So those are some general diagrammatic representations. Let's try some questions now. Pause it if you want to read. List the members of the set A intersect B. I'm going to do a very quick diagram. They're not always necessary, but it sometimes helps me to see. So here's A and B. What do they have in common? They've got a 1 in common. They don't have a 2 in common. They do have the 3 in common. So that's a little illustration of the two sets and how they interact. So A intersect B is 1, 3. A union B 1, 2, 3, 4 and 5. Now the people that get the terminology mixed up regularly, systematically get these two the wrong way around. So learn it properly, and it's got a very high success rate, this topic. Explain clearly this meaning. So 3 is a member of set A. It's simply just vocabulary and learning it. Some more notation. So this tells me that R is a subset of P. So I can add it to the diagram here. It's a topological diagram, so it doesn't matter how big you make it, so long as the relationships are preserved. Q intersect with R is empty. So Q and R don't overlap. But we don't yet know where Q is. It could be out here. However, the next piece of information says that when you combine P and Q together, P does not get any bigger. So the only way you can combine two sets and it not get bigger is if one set is inside the other already, because making the union of it makes no difference to its size. So Q must be in here, and we know from the middle information Q and R do not intersect. So that's my diagram. So we can see here, I mentioned earlier, that a set can be defined either by listing its members, if there's a few of them, or by stating the rule that they follow. Here you can see an example of infinitely large sets, so it's impractical to start listing them. So set A is multiples of 5, set B is multiples of 3, and the universal set is whole numbers or integers. A intersect B dashed, it's in A, but it's not in B. So that is this region here. Bit sloppy with my shading. It's this region here. 3 members of the set A intersect B dashed. So let's look back at the context. It's a multiple of 5, but it's not a multiple of 3. So that would be things like 5, 10, not 15, could be 20, 25 but not 30, 35, 40 but not 45, etc. Set C is multiples of 10. Now let's think about it in context with set A and set B. All multiples of 10 are multiples of 5, so C is completely within A, but not all multiples of 10 are multiples of 3. So it overlaps with B, but it's completely within A. Putting those two things together means that C must be something like that. Again, it's a topological diagram, so the size of them does not matter as long as their relationships with other sets is correct. Now we want 3 members of A intersect B intersect C dashed. So it's a multiple of 5 and 3, but not a multiple of 10. So if it's a multiple of 3 and 5, it's a multiple of 15, but every other multiple of 15, because even multiples of 15 are multiples of 10. So 15, for example, 45, 75, but not 30 or 60. This is quite a nice question because it tests your ability to understand the notation, and also as you work bits out, other bits start to unfold. So let's unwrap it. There are 24 things in the universal set, and there are 8 things or members or elements that aren't in P. So this is my starting point. Let me look at the diagram. P dashed is the 3 and the W. So if there are 8 elements in P dashed, W plus 3 must equal 8. That being the case, W must be 5. So I can fill that in straight away. What else do we know? The number in P intersect Q complement is 15. P intersect Q is there. The complement is W, X and 3. So we know W is 5. So 5 plus X plus 3 equals 15. Which means that X must equal 7. We know now that there are 24 elements altogether, and so far we've got 5, add 7, add 3, add Y equals 24. This is 15, so y must equal 9. That's everything filled in. To now proceed to part B is now just identifying correct regions. P dashed intersect Q means it's in Q but not P, and there are clearly 3 elements in Q that are not in P. Straightforward. P dashed union Q dashed. P dashed is 5 and 3. Q dashed is the 7 and the 5 again. When we're taking the union, we don't repeat. So that is 15. We don't count repeats. The next one, it's in P, it's in Q, but it's not in P. Well, it can't be in P and not P as well, so there aren't any members in that set. A little bit less help here on this one. Let's label the 2 sets French and Spanish. I'll go through it algebraically and then show you a quick way that works sometimes. There are 31 students. We know that 17 study French and 15 study Spanish, but if I put the 17 and the 15, it's not telling us anything about how many do both. 6 students study neither French nor Spanish, so we know out here there are 6, and we know if there's 31, these 3 regions have to add up 25. So let me call the amount in the overlap x, then those that study French only will be 17 take away x. Those that study Spanish only will be 15 take away x. We know that these 4 regions add up to 31. 6, French only, French and Spanish, Spanish only equals 31. So if I now tidy that up, 17, 15, add the 6 is 38. Take away x, add x, cancel out and leaves you with a subtract x equals 31. Rearranging that, we get that x equals 38 take away 31. So the number in the overlap is 7. Now we're in a position to go back and answer the actual question. How many study only one language? Well, we have 17 take away x, which is 10 students. 15 take away x, which is 8 students. So how many study only one language? 18 students. Now the quick way of finding out the intersect is to simply add up the 17 and the 15. We know that if the 6 don't study anything language based, these 2 must add up to 25. We add 17 and 15 together, which comes to 32, but there can only be 25 students in these 3 regions, so that means we've counted 7 of them twice. That's the quick way of doing it. You'd still need to then go back and work out how many students study only one language. Another non-numeric example here. 3 sets A, B and C. We're told that A and B don't intersect because the intersection is the empty set. So B is out here somewhere. Topological could be written anywhere, it could be any size you want, so long as it does not overlap with A. And C is a subset of A. There we go. On the Venn diagram, shade the region that represents A intersect C dashed. So it's in A, but not C. It's this bit, it's the white of the egg. And just to finish off with, a slightly more extended question. This would be moving in, for those of you in the UK, this would be moving into an AS type question. An Edexcel syllabus, this is in the S1 module. Okay, you've taken that in. Let's label it up. So we've got biology, chemistry, and physics. Now with these sort of questions, it's always best to start in the middle and work your way out. Is there any information about all 3 subjects? Yes, there are. 3 students that study all 3. So that's that piece of information. If I move up now, 5 students study physics and biology. Physics and biology is this shape here. 5 altogether. I've got 3 counted up for already, so there's 2 there, making 5 in total. 11 students study chemistry and physics. That's this region here. I've got 3 already allocated, so the other 8 are there. 8 plus the 3 is the 11. 7 students study biology and chemistry. It's this section here, made up of these 2 regions. There are 3 here. There must be 4 there to make the 7 in total. That's all of my intersection information. Now I need to go to the whole set. 30 students study physics, and I have 13 of them here, so there must be 17 study physics only. 28 study chemistry, and I have 15 here, so there must be another 13 study chemistry only. And lastly, biology. I have 9 study biology plus something else, so there must be 11 study biology only. If I total all those regions up, I find that there are some missing. There's 58 accounted for here, and we know there are 80 students altogether, so there must be 22 that don't study any form of science. That's now my diagram completed. The rest of this question is based on finding the regions in here and expressing the probabilities. Find the probability that the student studies chemistry, but not biology or physics. So clearly it's these 13 candidates, 13 over 80. Find the probability that the student studies chemistry or physics or both, all of set C and all of set P, which, if you total them up, comes to 47, so the probability is 47/80. Given that the student studies chemistry or physics, so this is a conditional probability. If we know that we're only looking at chemistry or physics students, we know that there are 47 of those. Find the probability that the student does not study biology. Well, we're ignoring these 9, so there are 38 of them. 38/47. Okay, so I hope you found that quick tour through set notation useful. Subscribe, like, leave some positive comments. Thanks for watching.